Thank you for attending. Today I'll be presenting the work we did on improving the computational overhead of training adversarially robust neural network-based image classification models. And our work is called robust representation matching. And I'm going to start right away. So neural networks are continuously evolving. Right? This here is a plot taken from Papers with Code. And it kind of shows how the top one accuracy on the ImageNet dataset has improved over the years. And as you can see, almost every year you get a new architecture that kind of improves upon the previous ones and kind of further improves the overall performance of image classification models. Naturally, if a developer is using neural networks in their applications, with every new neural network architecture that is introduced, they have to kind of update their application. And this could probably be a very frequent update that they have to make. However, it is also commonly known that adversarial inputs exist that are basically imperceptibly perturbed versions of regular images that can induce worst-case behavior in neural networks. So in this case, a stop sign gets misclassified as a speed limit sign. In safety and privacy critical applications, this can be of great concern and can cause catastrophic consequences. So ideally, we would want our machine learning model to kind of behave reliably or consistently across all imperceptibly modified copies of a given image. So how can we do that, right? So there's adversarial training, which is to date one of the most effective ways for training networks to be kind of consistent or adversarially robust. In every iteration of adversarial training, you generate a batch of adversarial inputs using a process called projected gradient descent, or the PGD attack. And then you kind of update the network's parameters to minimize the classification loss on these adversarial inputs. Overall, adversarial training requires multiple forward and backward passes through the network every training iteration. Naturally, this makes adversarial training very expensive computationally. So for example, as compared to standard training, adversarial training requires about 8x total training time. Furthermore, this computational overhead of adversarial training scales poorly with the network size. So for example, a ResNet 50 network, which is about 2.5 times larger than a VGG11 network, would require about 12x more total training time to be trained adversarially. So from the model evolution perspective, if the developer wants to preserve adversarial robustness across generations of neural network architectures, they will have to kind of retrain every new network that is introduced with this expensive process of adversarial training. And as you can imagine, after a few updates, the cumulative cost will kind of compound, making adversarial training very kind of inefficient from this model evolution perspective. So some prior works have looked at ways to reduce the overhead of adversarial training. And first, we have a free adversarial training, which kind of approximates the process of adversarial training in such a way that you only need a single forward and backward pass per training iteration. And roughly how they do this is by kind of reusing the computations across successive training iterations for the PGD attack. And then there's fast adversarial training, which kind of uses the lessons learned in speeding up standard training and kind of apply them to adversarial training. Specifically, they use things like mixed precision training and cyclic learning rate scheduling to speed up adversarial training. So how do these methods compare to adversarial training, for example, quantitatively? So we have trained a ResNet 50 network here on the CIFAR10 dataset using all these three methods, and we're reporting their overall performance on unperturbed clean inputs and adversarial inputs, as well as the training time statistics. As we can see, fast adversarial training is about 9x faster than just vanilla adversarial training in terms of total training time. And free adversarial training is like 38 times faster, which is, this is the fastest. And clearly both these methods do a really good job at accelerating adversarial training. So I'm going to come back to the model evolution perspective, where our goal was to preserve adversarial robustness across generations of neural network architectures. If one were to use the existing methods, this would kind of entail retraining every new generation from scratch. And any older robust network will have to kind of be discarded without any further use. We envision that a better solution would involve getting more use out of the older generation network by kind of transferring its robustness to the newer generation architecture, and in process, kind of speeding up the process of robustly training the newer architecture. So why would this be a better solution, one might ask? Well, firstly, such a solution would require performing this expensive or like the state-of-the-art adversarial training-based method only once in order to kind of get a highly robust classifier. And then thereafter, you can just transfer this high robustness to all subsequent networks using some like a much cheaper training process. Or in other words, the older generation network can be reused to speed up the process of robustifying the newer generation networks, thereby getting more use out of the computation that you spent on the older network. So to implement our solution, we propose robust representation matching, or RRM for short. And this method enables transfer of adversarial robustness between networks. And the way it does this is by matching penultimate layer outputs corresponding to unperturbed inputs. So now I'm going to describe how RRM training works. So first, RRM requires an adversarially trained teacher. So for example, this can be an old generation network that was trained using adversarial training. And now to transfer this teacher's robustness to the newer generation network, which we call the student, we will train the student to match the penultimate layer outputs of the teacher on unperturbed inputs. In addition to this, we'll also minimize the classification loss on the unperturbed input. I mean, train the student to minimize the classification loss. So now one might wonder, how does matching penultimate layer outputs kind of result in the transfer of robustness, right? So some prior works have shown that adversarially trained classifiers have penultimate layer outputs that are robust. So therefore, if you teach a student to match the penultimate layer outputs of a robust network, it should inherit this robustness. Note that since RRM does not require any adversarial inputs during training, its cost is comparable to standard training. To evaluate RRM, we compare it against prior works mainly on the basis of two metrics. One is the adversarial robustness, and the second is the total training time required to achieve said adversarial robustness. And we compare against prior works on not only the accelerating adversarial training, the fast and free adversarial training, but also other methods that could potentially be used to transfer adversarial robustness. There's knowledge distillation, there's robust data transfer. And, but for brevity, as part of this presentation, I'm only going to be presenting results that compare against the acceleration prior works. For those interested, you can find a complete set of results and comparisons in our paper. All right, let's look at some numbers now. So we've already seen the first 3 rows from the previous slides corresponding to prior works. And now I'm going to add 2 new rows for RRM. One using VGG11 as the teacher, and one using a ResNet 18 network as a teacher. All right, so as we can see, RRM trained classifiers achieve comparable adversarial robustness as vanilla adversarial training. And compared to prior works, RRM achieves comparable adversarial accuracy than fast adversarial training, and about 4-point higher adversarial accuracy as compared to free adversarial training. Note here that unlike free adversarial training, RRM does not suffer with a drop in adversarial accuracy to account for the acceleration or the speed up. Yeah, so speaking of speed up, in terms of total training time, RRM is about 58x faster than vanilla adversarial training. And compared to the prior works, RRM is 6 times faster than fast adversarial training and 2 times faster than free adversarial training. So looking at this table, one might note that RRM and free adversarial training have kind of similar per epoch times because both of them are like comparable to standard training in terms of per iteration cost. However, RRM is faster in terms of total training time because it converges much faster in about like half the epochs as free adversarial training. One possible reason, so we provide evidence for this faster convergence in the paper if you're interested. But one possible reason for this convergence can be the fact that free adversarial training requires training from scratch, whereas RRM is reusing the information that was encoded by the older generation network, which kind of thereby helps it kind of converge faster. So further looking at the slide, one might wonder, how does free adversarial training and RRM compare if you fix the total training time? Or in other words, you give this, the same amount of total training time budget to both the methods. So how does the performance of both these methods look at in that case? To answer this question, we train a classifier using free adversarial training using the same number of epochs. And in this case, we can see that the performance drops significantly. And so in conclusion, we can say that RRM achieves better accuracy on clean and adversarial inputs in the same training time. So far, while comparing training times, we have assumed the availability of an adversarially trained teacher. When this is the case, RRM is outright the fastest way of training a new robust classifier. However, when a robust teacher is unavailable, RRM would require you to train one first. Now, let's consider the worst case scenario where a teacher needs to be adversarially trained every time a new generation architecture is introduced. What we show is that RRM can be used to accelerate the process of robustly training the new architecture even in this scenario. And the way we do this is by adversarially training a small network like VGG11 as the teacher and then transferring its robustness to a larger network like ResNet50. In this graph here, now we have added the teacher overhead to the total training time of the classifier for RRM. And as you can see, even on including the teacher's overhead, RRM is about as fast as free adversarial training. However, the scenario I've described is kind of not exactly practical. This is because the cost of adversarially training a teacher is a one-time cost. Once the teacher is available, RRM can then be used to robustly train arbitrarily many new classifiers robustly. And so you can safely amortize the teacher's cost. In conclusion, the goal of our paper has been to reduce the computational overhead of adversarial training-based defense methods. We propose RRM, a method that involves transferring the adversarial robustness of one classifier to another at a cost comparable to standard training. And our results indicate that not only does RRM-trained classifier achieve comparable adversarial robustness to the state-of-the-art, but they do so in the faster training time than the state-of-the-art. And our code is available on GitHub, publicly available on GitHub. And thank you again for attending, and I'll be happy to take any questions.